G'day again. Welcome back to Mathematics 302. Hope you're having a good morning or a good evening. This is lecture 6 and I'm split it into two parts. So this will be 6A. I'll just move my image out of the way there, just down the bottom, and we'll get into it. I'm not sure we're going to put in 6B. I did have a whole list, but I've cut them all out. There is a significant amount, and I'll just talk through this. I've got functions, the Bolzano-Weierstrass theorem. Now, to do the proof of that, what I realized while I was doing that was you needed to understand the nested interval property, which isn't actually on the schedule of things that you need to learn about. But if you don't know that, you can't do that. And the same with certain other things. So Cauchy criterion was fine because that's pretty close. Then you've got completeness, where you can't do that without doing incompleteness. And one of the really interesting things about completeness is they talk about Gödel's incompleteness theorem, and then to do that, you need to know Peano's axioms, which you may have studied before. So this is probably bigger than what the original plan was, but it seems to expand naturally, given that things are sort of interlinked. And there's a whole bunch of other things that I could link it to, but we'll stick with this to start with because that'll be enough. Okay, so let's go. So functions, you would have seen this in high school. The function is where there's a one-to-one relationship between variables, and you know the straight line methodology that you would have learned with graphs. So if we look at y equals 2x, if we put a straight line down there, it's only passing through one point. There's 1x for 1y. Same here, y equals e squared, e to the x. You've got one line going straight down. You say, yes, that's a function. Here you've got y equals ln x, same thing, you've got one line you can put vertically, and my image will be in the way for the last one. And here I've got y equals cos x. Now you notice here you can put a line straight down this way, but you can't put a line this way. So that is a function because you can put the line down this way. Okay, but there is more than one x to give an equivalent y. Okay. So if we look at in set theory, a function is where each element of a domain is paired with an element in the codomain. So we just go domain A, codomain B. Should be pretty simple. So we'll say 1, 2, 2, 4, 3, 6. So in this equation, B equals 2 times A. And they're never going to be equal. It doesn't matter if you go positive, negative. B equals 2 times A. This individual will never be repeated because once you've got a 1, you can't get anything other than 2. Same here. If we do B equals A squared, whatever you put here, you can't get a different value here. So if 1 can't give you a different value of 1, and 2 can't give you a different value other than 4. Now notice here, you can put in -3 and get 9, but you still can't repeat that 3. You can't get a different value over here for that 3. So let's compare that to if we do 1, 1, 4, 2, 9, 3, then you've got b squared equals a, which fails as a function as soon as negative is considered because now you've got 9 and 9. So you can't have the same first number for it to be considered a function within a domain. And really that's the similarity between graphs and set theory. Okay, and some easy examples for you. Is the following set a function? So you've got A is A, B, C, D, B is E, F, G, H, and F, the function of that, is A, E, B, F, C, G, D, H. So you just ask yourself two questions. 1, does the domain of F equals A? In other words, does the domain of this thing, this F, does this domain, are all the first elements of F equal to A? So what are the first elements? A, B, C, D. So there you go, A, B, C, D. Yes, that is A. Tick. That's the first thing. Secondly, are there any repeated values in the domain of F, i.e. in that first set of values of F? Are any of these repeated? Answer, no. Therefore, really easy, yes, it's a function. Okay, do a second one. C is X, Y, and Z, and D is L, M, N, O. And now F, the function of that is XL, YM, YN, ZO. And immediately your brain is ticking. Does the domain of F equal C? In other words, are all the first elements of F C? So you've got X, Y, and Z. So yes, the domain is covered, F is C. Are there any repeated values in the domain, i.e. the first elements of F? Yes, Y is repeated, which obviously you would have noted. Therefore, it is not a function. Okay, so they're very simple tests. Okay, so now we're going to move on to the Bolzano-Weierstrass theorem. I'm not sure if I said that correct, but hopefully close enough. Which is simply this. Every bounded sequence of real numbers contains a convergent subsequence. In other words, if you can bound a set of real numbers, if, for example, 1, 2, 3, 4, 5, so you've got a bound of 1 and 5, there will be a convergent subsequence. That's the theorem. So this means that even if an entire sequence does not converge, you can always find part of the sequence, a subsequence, that does converge to a limit. So if you've got an infinite sequence which doesn't converge, well, if you've got an infinite sequence which doesn't converge, you can always find part of the sequence that does converge. So that's what the theorem is saying. So let's solve a problem. First, we're going to prove the sequence is bounded. And second, we're going to use the theorem's proof logic. Now, this whole lecture, and possibly moving forward, a lot of it is based on proof logic, just on simple logic terms. So this can easily be expanded into computer logic. We won't do that at the moment, but it could easily go there. So proof logic, usually involving a repeated bisection of intervals or using properties of infima and suprema, you extract the convergent subsequence. So that's what you're doing. There's two steps. Bounded and then use the proof logic. So, problem one, prove that the set 1, a half, a third, a quarter, satisfies the Bolzano-Weierstrass theorem. Right, now notice that there are an unlimited number of elements. Right, this goes forever, and I haven't set the end. However, the greatest lower bound, say it properly, is 0, which is obvious, and the least upper bound is 1, so it does have bounds. So we've completed the first step. It is bounded. We can tell it is bounded because this will not get less than 0 because it just keeps halving. What is a valid limit point? Well, you can take anything as a valid limit point within there. So let's just choose a small delta of 0.01 around some limit point. Well, let's pick 0. So we're going to say 0 minus 0.01 and 0 plus 0.01. So we're choosing some small delta around a limit point. So we're going from 0 backwards and 0 forward. So now we've got minus 0.01 and 0.01. Now we know the limit 0, so it can't actually get here, but we're choosing a small range, if we've got our delta, around that limit point. Now, obviously in our head, we know it can't go here, but we know it can go here and it can go to 0. Now here's our logic. Since 1 over 100, which is this 0.001, is within that range, and we can see that 1 over 101 and all small values approaching 0 as n approaches infinity will also be in that range, and it converges to 0, then we can say that this whole thing satisfies the Bolzano-Weierstrass theorem. You could have done it equally the opposite way, but easier to do it in this sense, to go towards 0. So that's what you're doing. Show it's bounded, and then you're using the logic within the range to show that it's going smaller and smaller. That approaches 0 as n approaches infinity, and therefore it converges. And therefore, because we can say that, we can therefore say it satisfies the Bolzano-Weierstrass theorem. So that's how it works. It's fairly self-evident where you're looking and go, oh, duh, that's obvious. But you've got to be able to just say that in point form to the examiner if you ask a question. And there is a YouTube clip on that. So there's a link for you. You can watch that. Problem 2. Prove that the set x equals 2, 4, 6, 8 does not satisfy the Bolzano-Weierstrass theorem. Greatest lower bound, 2. That's pretty obvious. Least upper bound is infinity. Problem. Therefore, since the upper bound has no limit, it's infinity, it cannot satisfy the Bolzano-Weierstrass theorem. You can't use infinity. You have to actually have an upper bound. So compare it with problem 1, where there's still infinite points, there's still infinite elements, but it's got an upper and lower bound. So you can still have infinite points. Here it just keeps on going, smaller, 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 but there is an upper and lower bound. So that's the difference. Hope that makes sense. So now we're going to do the nested interval property because we need that for the proof. So here's a line, and let's suppose that line is a bunch of numbers. Now here's half the set of numbers, and here's half again, and here's half again, and here's half again. And so what we're going to say is within that list of numbers, and I've drawn it as a line so you can see the line decreasing in size rather than drawing numbers all over the page. So we're assuming this is a set of numbers. So that we can say there exists an x which is not the null set, which is common to all intervals. So if we keep halving it, we can say there exists some x, because you can't keep halving it and get the null set, because you'll end up with some value x, and that value is common to all intervals because it'll be here, 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 here. It's still in every interval. So the nested interval property is in an infinite sequence of closed, bounded, and nested intervals has a non-empty intersection, meaning there's at least one real number common to all the intervals of the sequence. So by these green lines, I'm just representing a sequence of numbers by the green line to show you, halve it, halve it, halve it. You've still got this little bit in here. Okay, that's all that's trying to demonstrate to you. But this is the nested interval problem. In an infinite sequence of closed, bounded, and nested intervals, an infinite sequence of closed, bounded, and nested intervals has a non-empty intersection. So there's at least one real number common to everything. And image in the way, just go up. And if the length of the intervals approaches 0, then the intersection is a single unique point. So if the length of the intervals approaches 0, then the intersection will be a single unique point. There'll be one single point. And that's very important. Okay, so here we go. We've just made a picture. Again, this you can see this on another person doing a YouTube clip. Let there be a set of terms between m and minus m. So there's m, there's minus m, and here's a bunch of terms. Split the interval between minus m to 0 and 0 to m. So we're going to split the interval between this and this. Now, we're just assuming an unlimited number of dots here. What we're going to say is, on one side, not both, on one side, there's infinite terms. So if you split this and there's infinite terms, you can only say that on one half there's infinite terms. You can't say there's infinite on both sides. So if you cut it in half, you're going to say, okay, this is a fixed number, and then this is infinite. If the whole thing is infinite, then once you split it in half, one side will not be infinite. So we're going to say 0 to m has infinite many terms, and that's going to be I1. Now let's do it again. I2 from 0 to m on 2 has infinitely many terms. So now I'm going to put a line here and say, well, now I'm going to declare that this has infinitely many terms. Then I'm going to keep doing it. I3 is 0 to m on 4. That's got infinitely many terms. So this from here to here has got infinitely many terms. And the rest of the place hasn't. So every time I split it, I can say one side has infinitely many terms and the other side doesn't. And there's a YouTube clip there, you can watch that. So I to the k plus 1 will have infinite terms, and it will be half of I to the k each time. So by the nested interval property, there exists an x whereby, we should have whereby there, x is an element of ik, for all k which are elements of the natural numbers. So we can say let AN1 be element of I1, AN2 be an element of I2, AN3 be an element of I3, and these are nested intervals. So this gives us a subsequence. We've got these points on this, and the sequence is now AN1, AN2, AN3, boom, 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 and that keeps going. Now we're going to let some epsilon be greater than 0, so we can say that ANK, whatever this is, whichever one we pick, doesn't matter which one we pick, minus x is going to be less than epsilon. So since we're halving intervals, remember the picture, we're halving intervals, and the length of any sequence of a half to the n approaches 0, this implies epsilon will become infinitesimally small, right? This epsilon will become infinitesimally small, really, really, really small. And therefore, ANK minus x less than epsilon will become ANK approaches x, because these will have to approach each other because this is getting close to 0. So these will have to get near each other. And that's it, we're done. That proves it. That is a proof of the Bolzano-Weierstrass theorem. It is not like it's not much, but and sort of a bit self-evident and calling upon itself, but that is the proof of the Bolzano-Weierstrass theorem. Okay, the Cauchy criterion. You'll notice it's very similar. So let's consider the following sequence in graphical form: y equals phi equals 1 over x, which is this. And I've just put dots there. We can see that as y goes to 0, that y goes to 0 as x goes to infinity. So as this goes to infinity, so as x going to infinity, then y will get closer and closer to 0. That's self-evident. How can we show that a sequence converges without knowing its limit? Now you know this limit, but let's suppose you don't know what it is. How can you show it converges? Well, in this instance, pretty simply, if we take the first 3 terms, that one, and that one, we can see the distance apart is getting smaller. We can then take the next 3 terms, that one, and that one, and see that the distance between them, in terms of the y value height, is getting smaller and smaller. And that's how we do it. So a sequence is considered Cauchy, not kosher, if for all epsilon greater than 0, there exists some n such that am minus an is less than epsilon for mn is greater than n. Okay? And again, there's a YouTube clip you can watch if you want to watch that one. The other thing you need to know before we continue is what's called contractive conditions. So, let me just down. A sequence is contractive if there exists a constant c such that 0 is less than c is less than 1, so it's some fraction or some decimal. For all n elements of the natural numbers, the inequality xn plus 2 minus xn plus 1 is less than or equal to c xn plus 1 minus xn, as long as that holds. So it's considered contractive if this is true. So that's the condition of being contractive. This means that the difference between consecutive terms decreases by at least a fixed factor of c with each step. That's the contractive condition. So that's just to keep in mind. And a Cauchy criterion example. A sequence is convergent if and only if its terms eventually become arbitrarily close to one another, meaning the distance between any 2 terms after a certain point can be made smaller than any given positive number, epsilon. So let's consider 1 over n is 1 over 1, 1 over 2, 1 over 3, 1 over 4, and we're going to show this as Cauchy. It's very simple. So you're going to pick something. There exists some n such that an minus am is less than epsilon for all m and n greater than n, so greater than some value. So we're going to say epsilon is 1 over 10. Right, there's our epsilon. So we want to show there exists some value such that this is true. And all we're going to do is we're just going to go 1 over n minus 1 over m is less than 1/10. So we know 1/10 is in this. we've now got to find 1 over n minus 1 over m, because that's the sequence, is less than 1/10. Pretty simple. Let's just take some smaller numbers, or as it gets further and further. 1 over 22 minus 1 over 21. What's the value of that? Well, that's approximately, not exactly, approximately 2 over 100. That is less than 1/10. Therefore, the sequence can be considered Cauchy. That's it. That's as simple as it's got to be. You pick something along there, you go smaller, next one, next one. You could do 11 and 12 if you wanted to. I've just picked 22 and 23, sorry, 21 and 22 to move it further and make it smaller and smaller. So we can say that because that is smaller than this value, the sequence can be considered Cauchy. Okay, so it's a fairly straight way to show the Cauchy criterion. Completeness. Okay, last of all, we'll do completeness, which involves a few other steps. Completeness is where there's an ordered set, like real numbers, where every non-empty subset that is bounded above has at least an upper bound, has a least upper bound, a supremum, and every non-empty subset that is bounded below has a greatest lower bound, an infimum. Okay? You could have probably simplified that without using non-empty subset twice. For example, consider the set of rational numbers whose squares are less than 2. There's no least upper bound, since you can keep on creating numbers which have squares closer and closer to 2, and this tends towards an irrational number. So therefore, the set lacks completeness. So that is not complete. Incompleteness. So there's Gödel's incompleteness theorem, and this is where you really start getting theoretical. Any consistent formal system F within which a certain amount of elementary arithmetic can be carried out is incomplete, i.e. there are statements of the language of F which can neither be proved or disproved in F. Okay, might have to say that a few times, so let that sink in. As an example of the incompleteness theorem, a particular sentence G, the Gödel sentence of Peano arithmetic, is not provable nor disprovable in Peano arithmetic. So there's some sentence that we've got, this Gödel sentence, in Peano arithmetic. It's not provable or disprovable in a Peano arithmetic. The next question you're going to ask, sir, can you just remind me what is Peano arithmetic? Sure, no problem. Let's do that now. So Peano's axioms, 0 is a number. If A is a number, the successor of A is a number, successor. 0 is not the successor of a number. Two numbers, say that 3 times fast, are two numbers in which the successors are equal, are themselves equal. And then you've got this induction statement. If a set S of numbers contains 0 and also the successor of every number in S, then every number is in S. And that's the induction. So the natural numbers are 0, 1, 2, 3, 4, 5, da, 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 all the way up to infinity. So that's Peano's axioms for natural counting numbers. All right, so keep that in mind. So here we go. I'm going to try and make up a Gödel sentence for Peano. Now, this is my best attempt to do it. So here's my Gödel sentence. There's no way to prove or disprove that there's an infinite number of primes in Peano arithmetic. All right, this is Dr. Everett's Gödel sentence. I've made one up. So let's go through some logic steps to prove or disprove this sentence. In Peano arithmetic, which we just looked at, which is just those 5 axioms, there are an infinite number of natural numbers. True. Now that's obvious. There are more natural numbers than there are prime numbers, and that's also true. Since there are less prime numbers than natural numbers, there must be less than infinity of the prime numbers. Right? If you've got infinity natural numbers and there's less primes, there must be less than infinity of the prime numbers. Now that must be true. But you can also say there are infinite natural numbers, and since that is uncountable, there is also an uncountable, enunciate yourself correctly, an uncountable or infinite number of prime numbers, and that's also true. Can you see a problem with those two statements? Hopefully you can. Move image out of the way. Since both statements 3 and 4 cannot be true at the same time because they're in conflict, then the Gödel sentence is true. My sentence up here that I made for Gödel must be true, unless both of these are true at the same time, which can't because they're conflicting. Therefore, the system of piano numbers is incomplete. So what Gödel proved, and he looked at any and every set of numbers, was there's no such thing as a complete set of numbers because you could always find some set or some sequence that was not able to be proved or disproved within that system. And in this system, we're just looking at the piano numbers, which are the counting numbers. So that's my best effort to show you a Gödel statement by using piano. Piano is a very commonly used one, but that's my best effort. Okay, then I've created some homework for you for part A. If you can have a look at those, there's answers on it on the PDF. And that's all for now. I'll see you next time. Okay, God bless you, stay safe, and wish you the best. Okay, bye.